Okay, Intro to Derivatives, Unit 14. Again, if you're doing AB calculus next year, you will get probably this exact same notes packet at the beginning of the year. This will be our first or maybe even second unit. If you're doing BC next year, they're going to assume you know this, and we'll just jump in and assume you remember how to do this. And I think once we do it, you'll learn it, and it'll be fine. But BC people definitely need to know it. Obviously, you want to know it regardless because we're going to test over it. AROC and the definition of derivative. That's today. AROC is the average rate of change. There's a whole lot more to say about it, but you got to start somewhere. So we'll just start with average rate of change. The average rate of change of a function from x equals a to x equals b. So let's just say we got some random looking function. There's a and there's b, which means this is f of a and this would be f of b, so the y value's there. So the average rate of change, here's the definition that you'll need to know, is f of b minus f of a over b minus a. What's that? Yes. So this is kind of, I hope someone starts to realize, wait a minute, we've done this before. We didn't call it average rate of change. What did you call it? Slope. It's like Algebra 1 slope. And so there are questions, even on the AP calculus test, that say find the average rate of change of blah, blah, blah. It's well, yeah, you could have done that in 9th grade if you just knew that was the name of it. Average rate of change is the same thing as algebra slope. Good old y2 minus y1 over x2 minus x1. So, calculus books write it fancy like this, but yeah, it's just change in y over change in x. It's good old-fashioned slope. And so on the picture, that would be the slope of that line. Slope of that line. So example 1, find the average rate of change of that function from -1 to 3. So let's find f of -1 and f of 3. So f of -1 would be -5. F of 3, let's see, so that would be 3 squared is 9, 36 minus 9 is 27. And you probably remember from Algebra 1, it doesn't really matter which one you put first, as long as you put the same one first, right, when you're doing y2 minus y1. So I'm going to do 27 minus -5, which means I need to do 3 minus -1. So let's see, that would be 32 over 4, also known as 8. So that means the average slope from -1 to 3 is 8. The average slope, the average rate of change, the m, the dy dx, all that's the same thing. You don't really need to label it any of those things, but that's all the same stuff. All right, why don't you try example number 2? So change in y over change in x, and yeah, it doesn't matter which one comes first, as long as it's the same one coming first in the top and in the bottom. Average rate of change, slope, again, so it's super easy. There's nothing new about it other than maybe the name. I think we're starting to use this phrase in lower levels of math just so they'll be ready for it. Have y'all heard average rate of change before? Okay, good. All right, definition of derivative. Maybe the first thing we should say about a derivative is and this is where we get into the contrast with the average rate of change, is that a derivative is an instantaneous rate of change. The instantaneous rate of change. Frequently abbreviated IROC. Because we don't want to write out instantaneous every time. So instantaneous rate of change. But when you think about what that means on the graph, it's a little tricky. I'm going to draw that same picture. I'm not going to put A's and B's on it because we're going to use different variables for this one. But it's a little tricky to get an instantaneous rate of change. Because what do you have to have if you want to find the slope? 2 points. What does instantaneous rate of change suggest? 1 point. So yeah, another way to say this is like the slope at a point, which in algebra is not possible because you can't, like the slope formula requires 2 points. Like that's the whole deal. You got to have 2 points to have a slope. And now we're saying, well, we'd like the slope at that point, which doesn't really make sense. So instead we call it the slope of A. You know what I just drew there? You know the name of that thing?
Tangent line.
It's a tangent line. So the slope of a tangent line. Okay, so now we got to figure out some way to get that, like find the slope at 1 point, and yet the slope formula uses 2 points. So this is going to be a little bit weird. So let's call this x, and this is f of x. And we're going to come some distance away, so we'll come over here and we'll call that x plus h. All right, so we're going h away. Which means that that y value is f of x plus h. Okay, so the red one was a tangent line, because that's tangent to the curve. Do you know what that pink one's called? It has a special name too, that doesn't really fit with what you think, maybe. It's also a trig function. It's called a secant line. A secant line. We don't really use secant lines in calculus very much, because why would you use a secant line if you could use a tangent line? But it's a starting point, right? Like, let's start with our secant line slope. Let's call it secant slope. So that's good old-fashioned algebra 1. Like, we're not doing anything crazy yet. We'll get there. When we get to 1 point, that's crazy talk. But a secant line we can handle. So that would be f of x plus h minus f of x all over, let's shortcut that, the bottom. What's the delta x in the bottom? What's the change in the x? Just h. That's a difference quotient, and that's why you've been doing difference quotients off and on for a couple years, and you're like, why are we doing this difference quotient? What is the point of this? This is the point of it. It's a small step on the way to the definition of a derivative. So yes, this is the difference quotient. Okay, but that's still not a derivative, because that's not the slope at a point. That's the slope of this weird looking secant line. So what would make our secant line get closer and closer to our tangent line? Like, how could we make our secant line a better tangent line? Change in h. And what could we do? Like, what would be the best value of h to use? What's that? 0. Except that if we make it 0, then you've got 0 minus 0 over 0. That doesn't really work. What if we use this idea that we've just talked about?
A limit.
What if we use the limit
As approaches x
as
on the right.
Nah, even more basic than that. We want h to get smaller and smaller, so let's just do the limit as h approaches 0. Because as h gets smaller and smaller, so we're like it'll approach x, and that secant line will approach our tangent line. Yes? So it's going to be the same slope, except now we got a limit out in front of it. Limit f of x plus h minus f of x all over h. So it's sort of like the limit of the algebra slope. If we let the denominator shrink way down to super, super small, then our secant line turns into our tangent line. And that is the derivative. The symbol for that is a little prime on the f. So we say f prime. So that's the derivative. That's the instantaneous rate of change. That's the slope at a point. That's the slope of a tangent line. When you get to calculus, there's like 2 or 3 more words and phrases we use that basically mean find the derivative. Okay, so if I just throw the equation at you, excuse me, maybe that looks weird, but if you understand where it comes from, well, it's just good old algebra slope, but I don't want a secant line. I would like a really good algebra slope, so I'm going to let that h difference go to 0, and then my secant line turns into the slope of a tangent line. Okay, there's more to do, and we'll do some examples, but that's the thing for today. That's the main thing. That's the definition of a derivative. Limit as h approaches 0 of the slope. All right, turn the page. And realize that where we were using h, this person was using delta x, like change in x, and that probably makes even more conceptual sense. Like you can have a little bit of a change in x, which is going to change your function a little bit. But this is the same thing we wrote on the previous page. And different books use h and some use delta x. Okay, a little note on notation here. Different notations for the derivative of a function. Depending on how we want to use it, sometimes it doesn't matter. They're all the same thing. So, all of these mean the same thing. The derivative of y with respect to x can be dy dx, can be d dx of y. That sort of means take a derivative of y. This is the derivative of y with respect to x. And the prime is kind of the shortcut that means derivative. And you know that we use y and f of x basically interchangeably. They mean kind of the same thing. And so you replace all the y's with f of x's, and you got the same set of things. So all 8 of those things mean the same thing, mean derivative. So those 8, plus we can use the words like find the derivative, find the slope of a tangent line, find the slope at a point, or any of these 8 things. So that's 11 different things we could ask. That's really all the same thing. All right, example 1. Given g of x equals that thing, find g prime of x. Okay, so this is a bit of a process now. That was all concept. Now it's more like, what's the process of finding each of those pieces? Well, g prime, I'm going to write it out again here. So limit, I don't know, do you know enough to have a preference between delta x and h? Delta x it is. Delta x approaches 0, g of x plus delta x minus g of x over delta x. Delta x is certainly easier from a concept point of view, because visually what's happening is you're changing by a small change in x. After you've done it a bunch, you'll get tired of writing triangle x and would rather write h. So whenever you want to make that swap is fine. Okay, so I have a g of x I know. I got that. They gave me that. Check, check. G of x right there. But I need to find g of x plus delta x. So that means in place of x goes x plus delta x. And that's why there's a third of a page there, because there's some algebra to be done here. It's got to FOIL and distribute and subtract, like terms, all those things. So let's see, x squared plus 2x delta x plus delta x squared minus 2x minus 2 delta x. Our calculus concepts are over. Now we've switched over to algebra. Dia? Okay. So let's distribute the 3x squared plus 6x delta x plus 3 delta x squared minus 2x minus 2 delta x. Do you see any like terms? I hope not, because I don't. I mean, I wish we did, because it'd make life a little easier, but there's no like terms in there. So I've got to put all of this in for g of x plus delta x. So, limit delta x approaches 0. All of this goes first. 3x squared plus 6x delta x plus 3 delta x squared minus 2x minus 2 delta x. Minus, and let's make sure we put it all in parentheses so that we get it all, or so that we subtract it all, 3x squared minus 2x. And all of that is over delta x. Isn't this fun? Now do we have any like terms that we could cancel? 3x squared will go away. And the 2x will go away. Yeah, careful with the signs. Distribute the minus. That becomes plus. We'll cancel with that one. A little side note, when you're doing this process with polynomials, all of this stuff will cancel. If it's a polynomial, everything in here should cancel. You'll have a mess on the first part, but everything in g of x will cancel. Okay, some of you are going to start canceling now. I'm going to slow it down. It's the first one, so I'm going to rewrite it. Again, after you've done this a couple times, you'll see what happens, and you won't rewrite this step, and that's okay. So I'm just rewriting it after I canceled out the terms, and those are gone. Oh, speaking of canceling, what can we do here? Okay, I heard it phrased two different ways. Someone said I could factor out a delta x and then cancel. That's fine. Someone else said, well, I can just cancel a delta x from all the terms. Same thing, different way of looking at it. I'm going to guess you're probably comfortable with canceling with each of those. What's that? Make it a... Yes, but that's a good question. Wouldn't it make it a whole? But we're doing the limit as delta x approaches 0. So yes, there'd be a whole where delta x is equal to 0, but the limit means we don't care that there's a hole there. We just mean we're getting closer and closer. So that's a great comment. It would make it a whole. Let's be careful on this term because, and again, some of you are going to start skipping steps. I don't want to do that yet. 6x plus 3 delta x minus 2. Okay, so we took care of the holes, one way to phrase that, by canceling that out. Now we can substitute Be careful, delta x goes to 0, so we're only going to plug that into delta x, right? There's an x sitting there, but that's not the same thing as delta x. So if I plug that in, then that term goes away, and I get 6x minus 2. And that is my derivative of g. That means that would tell me the slope at any point along g. I would plug in x and get a number, and that would tell me the slope at that point. Okay, so there are definitely two distinct things going on here. The first thing is the calculus concept of this idea of secant line, algebra 1. We don't really want an algebra slope. We want a slope at a point. So we have to use this limit process. That's calculus. That's the big picture what's going on. And then when we go to apply that, then we've got algebra all the way down until we finally get to do, I guess that's calculus, but all you're doing is plugging in delta x equals 0 to get an answer. So, yeah, today's important because there's a lot of calculus and a lot of algebra going on. Now, some of the algebra you can skip. Please show me some stuff along the way. Don't be like, yeah, I did it all in my head and there's the answer. Like, well, show me some stuff. Again, a lot of you are going to cancel things like all in one step, and that's fine. But at least show me that step, and then however much until you get to the bottom after that. Okay. Same process, obviously a fraction, so this will be a little different. Let me write it out one more time. dy dx is the limit as delta x approaches 0 of, I guess I'll use y since we're using y's here, y of x plus delta x minus y of x all over delta x. You don't have to rewrite that every time because that is the definition. But writing it a couple times while we're learning it, just the process of writing it helps get it in your head. Once again, they gave us y of x, so we know that. Our job is to find y of x plus delta x. Okay, so 1 over x plus delta x plus 1. So I guess I'd say the initial algebra was a lot easier on this one because I didn't have to FOIL or distribute anything. Don't get too excited about the ease of the algebra though. So limit as delta x approaches 0. So of the orange thing, 1 over x plus delta x plus 1 minus 1 over x plus 1. Keeping track of the color coding here. That's the orange thing minus the pink thing all over delta x. Yeah, now you can have a frustrated look because now the algebra is kind of yuck. I don't like fractions and fractions. So let's multiply the top and the bottom by all the denominators so that all the denominators will go away. So that means I get to multiply by x plus delta x plus 1 and by x plus 1. And of course you can't just do that to the top, that would be illegal. You also have to do it to the bottom. Okay, so on the first term, the big term cancels, and we're left with x plus 1. Right, I'm not going to write it all out because it's just too much. On the second term, the x plus 1's cancel, and we're left with minus, careful with the minus because it's got to go to all of that, x plus delta x plus 1. And then in the bottom, remember this is where we don't cancel or don't distribute anything. We're just going to leave it like this and hope something works in our favor here in a minute. Okay. How about the top? What can we... Oh, we can definitely combine like terms in the top. And it's not just combining like terms. Yeah, x minus x goes away. The 1's go away. And I'm left with negative delta x in the top. And then in the bottom, delta x, x plus delta x plus 1, x plus 1. Now, I got a little lazy here. I'm going to put it back in a moment. Officially, I should be writing limit as delta x approaches 0 on all of these. But if you leave it off, as long as you stick it back at the end, you'll be alright. Okay, anything else we'll cancel? The delta x's will go away. So limit as delta x goes to 0 of negative 1 over x plus delta x plus 1 times x plus 1. Cancel the delta x's, so that shouldn't be a problem anymore. Now we can substitute again. And we get negative 1 over x plus 1 times x plus 1, or just negative 1 over x plus 1 squared. Okay, so the calculus concept is not that bad. It's... Uh-oh. That's why Miss Mary took a long time. Time to get out of here. 9:50. Let's keep rolling. Alternative form. This is, in some ways, is even easier. Let's do, I guess we do the same. Well, it's the same thing, except instead of, so it's still, although I probably want to write that the other way, but so here's the algebra slope, f of x minus f of a over x minus a. This time though, I want to find the tangent line at a. So I would really like for x to get closer to a. X, if you'll go to a, then I'll have my tangent line. So there's my alternative form. The trick is the alternative form gives you the slope at a particular point. At a point x equals a. Flip back. The definition of the derivative gives you the slope at any x. And that's the big difference between the two. So the bigger generic form works for any x, and you get an equation that you can plug in any x you like and find the slope at that x. Alternative form is a little easier and cleaner. The trouble is it gives you the answer at one spot, and you have to repeat the whole process if you want it at a different spot. So, example 1. F prime of 2. In fact, you know what? Let's put a f prime at a. So that's one specific point, one particular point. Only one point, however you want to phrase that. So alternative is nice but you only get a narrow answer. You get one answer. The bigger one takes longer, but then you've got a derivative that works anywhere. Okay, so kind of same process. F of x, we got that. That's nice. So I need f of 2. That's pretty easy. Just plug in 2. Let's see. 8 plus 8 minus 3 is 13. Yep. So f of x is 2x squared plus 4x minus 3. F of a, in this case a is 2, minus 13, all over x minus 2. The limit as x approaches 2. We skipped over this last. We did them last. I'm supposed to substitute first, but I'm always going to be getting 0 over 0 until I do an algebra trick. So let's see. 2x squared plus 4x minus 16 over x minus 2. Let's factor out a 2. Again, I'm being lazy with the notation here. Shame on me. I'll put it back in a minute. Factor out a 2. Then I can factor what's in there. X plus 4 and x minus 2. Aha! What do you know? The x minus 2's cancel. So yes, that puts a hole there, but we're not worried about a hole because we're just talking about limits as x approaches 2. So I can now substitute 2 in for x. 2 times 2 plus 4, 2 times 6 is 12. So the slope at 2 is 12. So the alternative form is quicker, maybe, easier usually. And if you only want the derivative at one point, it's probably preferred because it's quicker and easier. But then if I ask you for the slope of this thing at 3, you'd have to go back and do the entire thing again. And for the slope at 4, you'd have to go back and do the entire thing again. Whereas if we'd have done the big definition, we could just plug in 2 or 3 or 4. So kind of depends on how the question is worded as to what it wants you to do. Example 2 is the same thing. I'll set it up and then we'll stop there. So y of 3 would be 2 times 27 plus 1, 55. So looking back at my definition, I want the derivative at 3 would be the limit as x approaches 3 of y of x 2x cubed plus 1 minus y of 3 55 all over x minus 3. Maybe that looks terrible, but 2x cubed minus 54, and then you factor out a 2. That leaves x cubed minus 27. Be careful how you cancel that, but after you factor, then you can cancel, and then you plug in 3. Oh, may as well, we're almost there. X minus 3, x squared, plus 3x plus 9 over x minus 3. X minus 3's cancel. We plug in 3. Yes, I'm going fast. 2 times 9 plus 9 plus 9 is 54. And yes, that is right. That's the slope at point 3. But you can see it. Sorry. Assignments worksheet 1, I'll pass that out to you now.